So good afternoon, everyone. My name is Yew-Soon. Currently, I'm a senior research scientist at Agency for Science, Technology, and Research in Singapore. So today it's really my honor to present our research paper, Adaptive In-Context Learning with Large Language Models for Bundle Generation. So product bundling has evolved into an important marketing strategy to promote products catering to both physical and offline retailers. So typically, the bundle refers to a group of items that are recommended or sold together as a package. And these products are bundled together due to various reasons. For example, they may have alternative or complementary relationships. So for example, if a user is shopping for a camera, and the bundle recommendation will recommend not only the camera itself, but also the lens, the camera bags, and memory cards, all packed together at a discounted price. So in this sense, product bundling can bring beneficials towards both customers as well as the business. So for instance, it can help the customers to discover new products and prevent the formation of the filter bubble, and thus provide long-term enhanced user experience. And regarding to the business, it can help increase the product sales and boost the revenue, thus promoting the overall economic growth within the society. So in summary, product bundling can be considered as a win-win solution. However, after a comprehensive literature review, we find that most of the existing studies, they assume the pre-existence of the bundles and directly dive into the downstreaming tasks like the bundle recommendation, and they directly take the co-consumed products or user-generated lists as a synthetic bundle, or they rely on the manually predefined bundles by retailers. And although there are some studies focusing on the bundle generation, they suffer from several limitations. For instance, they may be able to generate fixed size of bundles or single bundles per user, and most importantly, they overlook the consistent user intents behind all the products within a bundle. And generally, the products in a high-quality bundle should reflect a same user intents that is semantically interpretable to the users. So without such a constraint, the generated bundles may be less relevant and intelligible to the users, thus failing to meet their requirements. So to address this challenge, therefore, we propose an adaptive in-context learning paradigm by leveraging the self-reflection and reasoning abilities of large language model. So we propose to perform two interrelated tasks that is generating the personalized bundles as well as inferring the underlying user intents. So this is motivated by the fact that the users are more inclined to explore relevant products, either as alternatives or complements based on their specific intents during a session. Okay, so this is the overall framework of our proposed adaptive in-context learning paradigm. So it mainly consists of three components. So first of all, the neighbor session retrieval. So in this module, we aim to use the retrieval augmented generation to find out the nearest sessions for the target session, and then we create prompts to instruct the large language model to perform both tasks. And then the second module is the adaptive demonstration generation. So in this module, to improve the reliability and mitigate the hallucination, so we first propose the self-correction module, which is used to foster the mutual enhancement of the two tasks without any supervision signal. And then to further guarantee the performance, we also designed an auto feedback adaptation mechanisms, so which is used to supervise the signals to the large language model, so by comparing the large language model's output with the ground truth label. And then finally, we instruct the large language model to summarize the rules derived from the whole task execution process. And then the third module is the demonstration guided inference. So in this module, the two tasks on the test session is performed by observing the demonstrations of its neighbor session. So because different neighbor sessions may have different mistakes made by the large language model, thereby they will receive different feedbacks and tips. So this will allow the test session receive tailored and customized lessons from the closely related task for further improvements. Okay, here let me use a very simple diagram to show the whole process. So given a test session, and then we leverage the retrieval augmented generation to find out the nearest session for the test session, and then we get the large language model to perform the two tasks on the neighbor sessions. So first of all, we leverage the reasoning capabilities of large language model to infer the bundles and then the intents behind it. And the second, the self-correction module is used to iteratively update the intents and the bundle based on each other. So because these two tasks are mutually enhanced. Okay, and because only with the unsupervised signal we cannot guarantee reliable results. So in the third step, we design the auto-feedback adaptation mechanisms, so which is used to provide the large language model with different feedbacks. So this process is achieved by comparing the ground truth as well as the response generated by the large language models, and we can provide different types of feedbacks to the large language models depends on their response and the ground truth. So you may refer to our papers for the detailed types of feedbacks for the generated bundles and the intents. And so this process is iteratively done. And the last step, we instruct the large language model to summarize the tips for the whole process. And finally, so the test session is able to observe the demonstration and do the inference for the two tasks. So as we mentioned, because different neighbor sessions may have different mistakes made by large language model, thereby receiving different feedbacks and tips. So in doing this, it will allow the test session to receive the customized and tailored lessons from its neighbor session. Okay, and regarding to the evaluation, we adopted 3 bundle data sets. So these data sets were released in our previous SIGIR paper in 2022, which is a resource paper. And the 3 data sets were constructed based on the public Amazon data set. So we launched a crowdsourcing task to ask the workers to label the bundles as well as the corresponding intents within each session. We also compare with 4 types of baselines: the traditional based one, the reinforcement learning based method, transformer and large language model based methods. And to evaluate the quality of the generated bundles, we adopted 3 metrics: precision, recall, and coverage. And to assess the quality of the generated intents, we conduct a human evaluation in terms of 3 aspects. The natureness means whether the intent is difficult or easy to read and understand. And the coverage means how many items in the bundles are covered by the intents. And the last one is motivation. So whether the intent contains motivational description. Okay. And here is the results. So the table shows the performance of all methods on the bundle generation task. So compared with the non-large language model-based methods, so normally the large language model-based method achieves better performance. And in terms of the non-large language model-based methods, the frequency, which is based on association rule, achieves the best performance in comparison with the rest 3 model-based methods. So this is mainly because of the data sparsity issue, which makes the model-based methods undertrained. And regarding the large language model-based methods, T5 with smaller parameters achieves the worst performance, and few shot outperforms their shots, and this verifies the usefulness of the demonstrations. Generally, our proposed methods achieve the best performance in most of the cases. And the figure here shows the results for the human intent evaluation, human evaluation on the inferred intents. So the bar means refers to the mean value, and the horizontal line here refers to the standard deviation values. So from the figure, we can observe that our proposed methods normally achieve the best performance, either with large mean value or smaller standard deviation values. And similarly, field shot outperforms their shot. And interestingly, we find that the ground truth that refers to the intents labeled by the cross-sourcing workers. So their performance is outperformed by at least one of the large language models in most of the cases. So the possible reason behind, we guess it should be the cross-sourcing workers may prioritize the speed of the task completion while sacrificing the quality of their works. Okay. And we also conduct an evaluation study to verify the efficacy of our proposed methods. And we compare with a number of different variants. So for example, we replace the top neighbors by randomly sampled neighbors, and we remove the self-correction module, the auto-feedback module, and both of them, and remove the summarized rules as well as the intent inference. So the results here verifies the efficacy of each modules in our proposed model. And lastly, we also investigate the impacts of the important hyperparameters on our proposed model. So TB here refers to the runs of the auto-feedback adaptation. So from the figure, we can observe the best performance is achieved around 4. Okay. And the figure here shows a case study. So we sample a test session from the electronic domain, and this is the ground truth. So that means the bundles as well as the intents annotated by the cross-sourcing worker. And the following are the results generated by different large language models. So the last one is ours. So generally, we can see our proposed methods performs better than the baselines, especially for the motivation of the intents. So for example, upgrade your streaming experience is more motivational than, for example, the streaming box and streaming players. Okay. Lastly, let me briefly talk about the limitations of our proposed framework. Because the framework is based on large language model, it takes advantages of large language model. Also, it suffers from the inherent issues of large language model as well. So first of all, we find that the average bundle size generated by the large language model is smaller than the bundles, the size of the bundle generated by the cross-sourcing workers. So here, GT means the ground truth. The bundles generated by the cross-sourcing worker. And although we find that our proposed methods may generate some bad case, so the bad case refers to the number of sessions with hallucination issue. So although we have added some hard constraint to ask the large language model to generate bundles with no less than 2 products. However, it still sometimes generates bundles with only a single product. But from the results, we can see that this issue can be partially alleviated by using more powerful language model like GPT-4. And here is a concrete case. So here we have a session, and this is the ground truth bundle identified by the cross-sourcing worker. And by using GPT 3.5, we can find that different large language models may generate hallucinations because they generate bundles with only a single product. While this issue is addressed by using GPT-4. Okay. Finally, let me conclude my presentation. So our study tries to address the limitations of existing product bundling study through the exploration of 2 interrelated tasks that is the personalized bundle generation and underlying intent inference based on the user sessions. And we propose an adaptive in-context learning paradigm which allows the large language model to take tailored lessons from the related tasks as demonstration. And finally, the experiments on 3 real-world datasets verifies the effectiveness of our proposed methods. Okay, that's all for my presentation. Thanks for your attention.
Thanks to the speaker. Any question?